Okay, today's lesson is going to focus on being able to take the derivative of inverse trig functions. So we already know how to take the derivative of sine, cosine, tangent, cosecant, secant, cotangent. We're going to talk today about their inverse functions, all right? So restricted domains for sine, cosine, and tangent in order to be monotonic, because remember, in order for a function to have an inverse that's a function, we have to have our original be monotonic. Well, monotonic means 1 to 1, always increasing, or always decreasing, which means that f prime is always positive or f prime is always negative. Okay, well, let's think about each one of these graphs. I'm going to start with sine. Our sine wave looks like this. And right now that is definitely not monotonic. Okay, never going to pass that horizontal line test. But instead, if I focused just from here to here, my function, sine, is strictly increasing. And that's happening from negative pi over 2 until pi over 2. And I picked this interval because it passes through 0, and we like to center things around 0 as mathematicians. Could I have picked this little chunk here? Sure, but now I'm starting from pi over 2 to 3 pi over 2. That just seems a little bit counterintuitive when we think about the number line. All right, so I've got sine situated, just that little purple portion. Next, I'm going to talk about cosine. Cosine's graph starts up high and goes low. So here's cosine, definitely not monotonic. But if I focus in just on this piece, that piece is strictly decreasing, which makes it monotonic. So from 0 until pi, if I could focus on just that part of cosine, that means that I'd be looking at a monotonic part of my function. So again, just that part in purple. Finally, tangent. Tangent has some vertical asymptotes going on. And tangent looks like this, and then it has that periodic nature to it, so it's just a bunch of repetitive stamps, right? Well, if I wanted to pick some part of that was monotonic, that covered the whole range, I would say one of those periods. So from negative pi over 2 to pi over 2, except this time I'm not including them, right? Like here I'm actually putting brackets on that interval. Here I would just be looking from negative pi over 2, that's a pi over 2, on the open interval, okay? So restricted domains for sine, cosine, and tangent, making them monotonic, okay? So again, monotonic, I've covered all of my range, negative 1 until 1, looking between 0 and pi without any repeats. Covering from negative 1 until 1, from negative pi over 2 to pi over 2 without any repeats. Negative infinity to infinity from negative pi over 2 to pi over 2, no repeats. Well, if those are the domains for sine, cosine, and tangent, then they should be the ranges for the inverse, right? Because in inverse, you just switch the domain and range. So for sine inverse, our restricted range is negative pi over 2 to pi over 2. That's a bracket. For cosine, our restricted range is going to end up being between 0 and pi. And for tangent, we're going to end up being between negative pi over 2 and pi over 2. Okay. Well, let's think about what that really means in terms of the unit circle. Everybody's favorite. So, sine on its own, its domain is everything. But restricted sine, we just said negative pi over 2 to pi over 2. And that's because the input is an angle theta, and the output is the ratio of the sides of the opposite of the hypotenuse over the hypotenuse. Well, if this is my domain, and this is my range, right? To find the inverse, I flip-flop those. So in goes an opposite over hypotenuse number, somewhere between -1 and 1, out comes an angle between -π/2 and π/2. So the output is now some sort of angle theta. For cosine, you take the cosine of theta. We're going to look between 0 and pi. That spits back for us the ratio equivalent to the adjacent over the hypotenuse. That's the ka part of SOHCAHTOA. Well, then the inverse, in goes a ratio, out comes an angle between 0 and pi. Tangent, in goes -π/2 to π/2 for our restricted domain. That was an angle going in. What comes out is a ratio of opposite over adjacent. In goes opposite over adjacent. Out comes an angle between -π/2 and π/2. Now, all of this is a review from pre-calculus. Remember that when you take the ratio of the opposite over the hypotenuse, you end up with a number between -1 and 1 because the hypotenuse will always be bigger than the opposite side. Same thing with the adjacent over the hypotenuse. But when you take the ratio of the opposite side over the adjacent side, nothing says one of those is bigger or smaller than the other, which is why we end up with this all reals situation. All right, more of a pre-calc review. Find the following without a calculator. Hint, think the unit circle. So into the cosine graph goes a ratio. Out comes an angle, theta, between 0 and pi. For sine inverse, in goes a ratio. Out comes an angle between -π/2 and π/2. For tangent, in goes a ratio. Out comes an angle between -π/2 and π/2. This one you can touch π/2 and -π/2. This one you cannot. Those are open circles there. Okay, so I'll help you get started. Cosine inverse a half is saying what angle, because we know our output is supposed to be a theta. What angle has a cosine value of a half? Cosine is the x value. Reference angles, that's going to be π/3. Now, is that 60 degrees? Sure, but we're in calculus, so we use radians. Go ahead and pause your video, see if you can remember from your unit circle how to evaluate these other three. Okay, here are my answers. These little check marks are just reminding you what quadrants you can draw in, right? So cosine you can draw in 1 and 2. For inverse, sine inverse you can draw in 1 and 4. Tangent 1 and 4. But then remember when we have negative values, you can't travel all the way around, because look at your restriction here. So instead of calling this angle that we want to say is 7π/4 for the tangent one, I can't call that 7π/4 because that means I went all the way around the circle to 7π/4. So instead of calling it 7π/4, I can call it backwards π/4. So -π/4. All right, find the following without a calculator. Hint, draw a triangle. So in these four, we're going to start with the inside and work our way out, but we don't have any unit circle special numbers, okay? So we can't just use our reference angles and our triangles that we're used to. Instead, we're going to have to draw our own triangle to reference. So looking at this right here, cosine inverse of -12/13. Well, cosine inverse I'm allowed to draw in between 0 and pi. Out of these two quadrants, where is cosine negative? That's going to be over here. So let me draw this reference triangle. And my cosine is supposed to be -12/13. So I'm drawing the adjacent over the hypotenuse. Here is my angle theta. Theta, this angle in green, whatever measure it is, I don't know its radian measure, but I know that it references a triangle whose cosine is -12/13. So now, what this new problem is asking me to find, it's saying, hey Schwartz, find the sine of theta. Cool, here's theta. Sine is going to require this side, and I know from geometry there's a 5, 12, 13 triangle. So what is the sine of this triangle, this reference, the sine is 5/13. Okay? I want you to pause your video, try these ones for yourself. Again, this is a review from pre-calculus. So draw these, and my hint is to draw a triangle for each one for that inner angle. Pause now. Okay, I'm going to talk you through the cosine of the tangent inverse of x over 4, and then I'll show you just the answers for the other ones. Actually, I'm going to show you the answers first. Look these over. And if you feel stuck on any of them, I'm going to talk through this lower left one down here. Okay, but pause your video on this slide if you need to look at stuff and edit. Don't just pause it to try to take more answers. All right, let's talk about this cosine of the tangent inverse of x over 4. Well, tangent inverse of x over 4 means I'm drawing an angle whose tangent is x over 4. I don't know if x is positive or negative. I'm going to default to positive, and I'll show you why that's okay in just a second. So I'm going to say, here's my angle, and I have a tangent value opposite over adjacent that's equal to x over 4. Cool. I had no idea what theta was, but boom, here's theta. All right, well, what am I supposed to find? I'm supposed to find the cosine of theta. Well, in order to find the cosine of theta, I have to find the adjacent over the hypotenuse. So I'm going to do a little Pythagorean theorem action. 4 squared plus x squared equals my hypotenuse. That was supposed to change colors. Hypotenuse squared, which means that my mystery side, my hypotenuse, is equal to plus or minus the square root of 16 plus x squared. But now, I know this is representing the radius of a circle because of all my geometry, right? Representing this distance, my radius always stays positive. So it's the square root of 16 plus x squared. Great. I was supposed to find the cosine. The cosine then of theta is the adjacent over the hypotenuse. 4 over the square root of 16 plus x squared. Okay? Now, the reason why it's okay that we drew this in the first quadrant versus the fourth quadrant, even though we didn't know what x was, notice that we're looking for cosine. And cosine would still be referencing this 4, and the same hypotenuse, it would just be down here. So our answer actually kind of takes care of itself in terms of how all the quadrants work for calculus, or for pre-calculus, sorry. So again, here's your answers. Similar thing, Pythagorean theorem found me this square root of 1 minus x squared, and then I wanted the sine of that angle. All of that was to prepare us to be able to do calculus. So how do we take the derivative of an inverse trig function? We are going to draw a triangle. Draw a triangle. The best angle to approach any challenge is the triangle. Ha 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 ha. Okay, I'm going to pause this video and start a second one with just the calculus part of things for today's lesson. See you in the next one.